When you hear the word Weber, what do you think of? Some people might think of barbecue grills. Other people might think of sliced bread. When I think of Webers, I think of the unit for magnetic flux. One Weber is equal to 1 Tesla multiplied by 1 square meter. So for example, if you were to take this ring and move it to the left or back to the right, let's go back to the left and maybe place it in a region where the magnetic field from this dipole magnet has a strength right here of exactly 1 Tesla. Well, then I guess the strength here is a little more than a Tesla, and here it's a little weaker. But right here, the strength is 1 Tesla, and then maybe this loop has a cross-sectional area of 1 square meter. Then you would have 1 Weber of magnetic flux for this loop. Well, it turns out Webers don't do much of anything. However, when there's a rate of change of the number of Webers, something significant happens. So we can say it in this way. We know that a Weber is a Tesla per square meter, but more significantly, a Weber per second is a volt. Now let's check that out a little more carefully. Let's see, a Weber per second would be the same thing as a Tesla times a square meter divided by a second. So the question is, what the heck is a Tesla once again? So if this equation is true, right, one of the first equations we learned in our study of magnetism, that the force on a moving charge has to do with the amount of charge, the speed, and the strength of the field. If F equals QVB, then B would be equal to F over QV. So a Tesla must be equivalent to a Newton per Coulomb times a meter per second. So let's make that substitution. A Newton per Coulomb meter per second replaces Teslas, and then we still have square meters and seconds to account for. So how do these units combine? Well, the seconds cancel out, one of the meters cancels out, and now we're left with a statement that a Weber per second is equal to a Newton meter per Coulomb. But a Newton meter, as you know, is a joule, and a joule per Coulomb, what's that? Well, yep, that's a volt. So, rate of change of magnetic flux is the key to this unit 4.3, which is our study of something known as Faraday's law. In particular, Faraday's law of electromagnetic induction. So if it's the Webers per second we're interested in, then I guess that says we can take the time rate of change of magnetic flux and say that that's equal to some number of volts, right? So by saying d dt, we're saying rate of change. Magnetic flux can be symbolized with the capital Greek letter phi, and so as not to confuse it with electric flux, we'll put phi subscript m. And instead of saying the rate of change of magnetic flux equals voltage, we'll say it's the rate of change of flux that induces a voltage. And here for voltage, we're going to go back to that symbol, that script-looking E that represents EMF, and electromotive force is just an old-timey way of saying voltage. So let's put this together another way and say d magnetic flux dt is equal to induced voltage. Well, that's almost right. Usually when we write this statement of Faraday's law, we transpose the equation. Okay, so that's not much of a change. EMF is equal to d flux dt. What we got wrong in this first statement, we left out an important negative sign. Now that negative sign has to do with something known as Lenz's law. Not Lens like the lens in your eyeglasses, Lenz. Lenz's law has to do with the polarity of the induced voltage. Now, I'll spare you the discussion of Lenz's law for now and just introduce it in name at this point and associate it with the negative sign in this expression for Faraday's law. Before we get to Lenz's law, it's time for us to play the game that's sweeping the nation called Flux, No Flux. So, here's round one of the game. You tell me whether or not this picture represents some amount of magnetic flux. You see the bar magnet, and now you see a loop of wire. Flux or no flux? Correct. In that case, there is some flux. Let's move to round two. Keep the same magnet in the same orientation and draw a different loop of wire. In other words, we've taken the first loop of wire and we've rotated it about an axis. Flux or no flux? Right again. This time, there's no flux. Okay, let's take this loop of wire and rotate it about an axis. Maybe we'll rotate it about an axis so that we view the loop of wire straight on, so we see its full circular shape. And we've also rotated the magnet. Flux or no flux? Right again. No flux. Okay, you're doing great. Let's move on to the last round. Flux or no flux? We'll put the loop of wire here. Do over. And what do you think? Flux or no flux? Yeah, we're back to having some flux. So you get the idea. As long as the magnetic field lines actually penetrate the area of your loop, then you have flux. So in case number 4, in case number 1, the magnetic field lines pass through the area of our loop of wire. But in case number 2, the magnetic field lines just skirt right past the loop of wire without penetrating it. And the same thing in case number 3, all the field lines are in the plane of the page, and the loop of wire is also in the plane of the page, and so there's no amount of flux in case 2 or 3. Well, flux has to do with the strength of the magnetic field and also the amount of area of the loop. Now, is area a vector quantity or not? Let's get into an argument or debate about that. I would say that area can be represented as a vector, and so if you had a loop of wire in the orientation shown, I would say that its area vector points in this direction. Some people argue and say no, area is just the scalar quantity measured in square meters, which could be found in this case if the loop is a circle. The area would just be pi r squared, and that would be a scalar quantity, end of story. So I guess we could agree if we introduce what we call the normal vector. So if we draw a line that's perpendicular to the plane of the area, and we keep that vector exactly 1 unit in length, then because that vector is perpendicular to the surface, we call it the normal vector, and because it's exactly 1 unit in length, we put the notation on top that says that's a unit normal vector. And so what we really mean by the area vector is the area vector is equal to the scalar amount of area multiplied by the normal vector. But I won't write it in this form. I'll just represent area as a vector quantity. And I need to represent area as a vector quantity because to properly calculate this quantity, known as magnetic flux, we need to know what the area vector is. Here's what I'm talking about. If you have a magnetic field pointing to the right in the plane of this page, now magnetic field is definitely a vector quantity, and that magnetic field doesn't exactly skirt past the area of the wire as it does in case 2, but then again it doesn't meet so that it provides a maximum amount of flux like it does in case number 1, Instead, in this special case, there's an area vector that's pointing at an angle relative to the magnetic field. So in that case, there is some amount of flux, and the flux is a scalar quantity calculated by taking the vector dot product of magnetic field and area. Or in other words, the magnetic flux is equal to the strength of the field times the amount of area multiplied by the cosine of the angle between the two. So if we were to rotate this loop of wire so that its area vector moved to a vertical position, then the angle between the area vector and the magnetic field would be 90 degrees. And what's the cosine of 90 degrees? 0, right? And certainly, when the loop of wire is in this case, then we have the condition of no flux. Now, if we rotated the loop of wire so it sat in this arrangement, then we would have maximum flux because the angle between the area vector and the magnetic field would be an angle of 0, and cosine of 0 gives us 1. So this is our formula for calculating magnetic flux. So we can state Faraday's law one more time. If d magnetic flux dt equates, negative d magnetic flux dt equates to the induced voltage, that's the same as saying negative d dt of the product of magnetic field and area. Or we might see it in this form. Induced voltage is equal to negative d dt, the integral of b dot dA. So where are we going to apply Faraday's law? Well, we can apply Faraday's law in a demonstration. I think the first demonstration I'll show you would be to take a loop of wire and move it back and forth in the presence of a magnet and show you with the use of a galvanometer that a very small electric current is produced by doing so. Now, alternatively, we could take the magnet and move it back and forth in the presence of a stationary loop. Either way, as long as there's relative motion between the magnet and the loop of wire, then a voltage is induced around the loop of the wire, driving a current around the loop of the wire. Another example would be to take the loop of wire and mount it on an axle. And then if we spun the loop of wire about this axis, there'd actually be no change in flux in this case, because spinning it about this axis would always keep the normal vector or the area vector pointing in the same orientation. So instead, we should imagine what would happen if we took the loop of wire and rotated it about this axis. Then the area vector would point to the right, and then a moment later point into the plane of the page, and then it would point back to the left, and then out of the plane of the page. And in doing so, we would change from having flux to no flux, back to flux and no flux, and there'd be a rate of change of the flux in that case, which is basically a description of how a generator works. And so in Unit 4.3, we're going to discuss how generators work. We'll make an example out of induction cooktops, guitar pickups, GFI circuits, that stands for ground fault interrupter. We'll learn of something known as motional EMF, and I think we'll conclude this unit with the discussion of how transformers work. But there'll be more examples along the way, so stay tuned.